as for this one, so Ian got his PhD at UCLA here. He's made a lot of interesting statistical visualization programs. In fact, won the John Chambers Award in 2011 for, no, that's the one you made for, is that for the statistical visualization or is that for the, all right. He also ranked second in the world competition for Texas Hold'em programs. So he was one of the second best poker bot in the world.
Alberta! University of Alberta beat me.
Which, keeping in mind, Alberta has a dedicated program for just game playing AI. So just by himself, basically competitive with them. Currently, he runs a statistical consultancy called Fellow Statistics. So if you have a statistical problem with your company, I think he's probably also a pretty good person to talk to. Certainly after this talk, you'll be even more convinced. And with that, here's Ian.
Thanks, Rob, and thanks everybody for coming out. Today we're going to talk about how to solve almost any maximum likelihood problem. And we're going to focus specifically on exponential families of distributions. So the basic outline is that we're going to sort of review what an exponential family is. They're everywhere. We're going to talk about the MLE problem and the basic algorithm for solving maximum likelihood when you can't actually compute the probability function. We're going to do some background on MCMC and friends, Markov Chain Monte Carlo, because I don't assume that everybody in this room is super familiar with that. And then we're going to talk about some of the practical things that you need to think about when you're actually trying to implement this stuff. Because if there's one thing that I've learned cutting the edge between mathematics and computer science, is that just because you can write down an equation or a formula doesn't mean that you can actually implement it in a way that's computationally tractable. We're going to talk about trust regions, better likelihood approximations, and then we're going to do a small live example. Okay, exponential families. So exponential families are everywhere in statistics and machine learning. And basically what you've got is if you have t, a random variable, and this can be massively, massively multivariate, basically it has to fit into this functional form, which is that it is equal to e to a parameter set eta times g, which is a vector valued function of statistics, plus o, which is an offset term. And then you have a normalizing constant c. And that normalizing constant is made such that the whole probability distribution sums to 1. So that's what you need to have a probability distribution. The problem comes is the normalizing constant is defined as the integral over all possible values of t of the numerator. And that integral, if t is massively multivariate, you run into the curse of dimensionality. You cannot compute that integral in a computationally tractable way. And it's actually been proven that the computation of that is an NP-complete problem in the general sense. If your t is categorical, you just replace that with a sum. Another important aspect is that there's an alternate parameterization. So we've got etas, which are our statistics, our parameters. But you can also think of it in terms of mu. For every eta set, there's also a mu, which is defined as the expectation of the graph statistics under the parameter set eta. And those are a one-to-one correspondence. And that will sort of come up. So that was the very general sense. Basically, exponential families are everywhere in statistics. Logistic regression, linear regression, almost every distribution that you'll see in your standard statistics textbook is an exponential family. And there are two things that make one exponential family different from another exponential family. The first is the the choice of statistics, right? So basically what you choose for your statistics. So for example, you have the uniform distribution over there, which just has a constant 0 times what the variate, makes it a uniform distribution. And that is compared with the exponential, which is e to the eta times t. So those are two different parameter sets, or two different statistics, and will give you two different types of distributions. The other thing that can make you different is the support, the values that t can take. So for example, the exponential distribution and the Bernoulli distribution down there, and by the way, these may look a little odd to you if you're used to seeing these written in a normal, sane way if you're actually thinking about these distributions, but basically it's just an alternate parameterization. So the exponential looks exactly the same as the Bernoulli. The only difference in these is that t is defined from 0 to infinity in the exponential, and in the Bernoulli case it's defined as either 0 or 1. So you can get vastly different probabilistic profiles depending on what your domain is. My research focuses a lot in networks and social networks, and so it's useful to define what a network is. Networks are nodes with ties possibly between the nodes, and basically we will define them as a connection, as the connections and then nodal variates. So the y here, let's say we have 18 nodes. If the ith, jth element is 1, then there's a connection between those two. If it's 0, then there's no connection. So for example, the first node has a connection to the fourth node, but it doesn't have a connection to the fifth node. And depending, this example is directed, so just because I have a connection to you doesn't mean you have a connection to me. And then we also have an n by k matrix of nodal covariates. And these can be things like age, gender, any sort of property of the nodes themselves. This example is binary, so it's either 0 or 1. But you can have multiple different ones with different domains there. You'll also see some sprinkled NAs here. Maybe you have missing data in your network. And if we have time, I'll get to how to deal with that, but we may not have time for that. So what do exponential families look like in network data? Well, currently, there are two main models that are used with network data. There is ERGM, which is exponential random graph models. And these are really heavily used in social network analysis, in determining the connections between individuals and creating a generative probabilistic model of those. And you see it just has its basic general exponential format. It's saying that the ties are random, conditional upon any nodal covariates that exist. So it's a distribution of the ties given the nodal covariates. On the other hand, Markov random fields, which are everywhere in statistical physics and are used in machine learning for things like image segmentation and image analysis, are a distribution of x with the y's considered fixed. For example, in an image, you might consider the y's to be a lattice, an n by n lattice. But the thing you'll notice is the functional form of these looks exactly the same. The difference is in the domain. These two vastly different models have vastly different properties, but they look pretty much the same on a superficial level. My dissertation research was focused on an extension of those, with subsuming those and saying, let's look at the joint distribution of y and x given just the parameter set. So looking at the sort of merging of those two, the joint distribution. OK, so we can write down those equations. But remember that C there, if I've got a network with more than, say, 4 nodes, I'm not going to be able to calculate that C. It's going to grow exponentially with the size of the problem. So I can't. So I've written it down, but I can't actually compute it. Geyer Thompson in 1992. That's two people, but I just run their names together. They basically said, okay, let's mess around with the log likelihoods a little bit. So take the log of that probability and look at, let's say, starting at an eta naught, eta 0, and looking at how does the likelihood improve as you move in different directions to an eta value. And if you look at the difference in those two log likelihoods, after you mesh around with it a little bit, you get eta minus eta naught times g of the observed statistics that you see in your observed network or data or whatever you have in your exponential family, minus log of e expectation at eta naught at the point that you're looking at of e to the eta naught times g of t. And then the first derivative is equal to g of the observed statistics minus the expectation at eta of g of t. So basically, if you set this to 0, right, which is what you want to do if you're maximizing something, what you're doing is you're setting your observed statistics, or you're setting your expected statistics, your mean value parameters, equal to what you observed in your data. So it's basically doing moment matching. That's what maximum likelihood is in exponential families. Okay, so we've written this down, but only two small problems. One, we can't calculate the expectation at eta naught because we can't calculate the probability distribution. And two, we can't calculate the probability we can't calculate the probability at eta either. So that makes it difficult. So suppose by some magic thing, which we're going to call MCMC, that we're able to have some samples. So we get k samples from the probability distribution. Well, the thing that we might think we can do is say, hey, let's take that log e to log expectation, and let's just plug in the sample expectation. And that we're going to call, so we're going to call the true one z, and we're going to call the estimated one in this sort of naive way as z hat infinity. And why it's called infinity, you'll see later. So great, now we have a method which we can estimate the log likelihood difference from eta naught to eta. So we can maximize that. The problem is that this guy, this quantity here, its variance increases as you move away from eta naught. So it's only a good approximation of the log likelihood around the neighborhood of eta naught, where you got your sample from. So that motivates a basic idea, which is, one, suppose we have, this is the basic Markov Chain Monte Carlo maximum likely algorithm. Supposing that we can sample from the distribution. Let's say we've got a distribution with two statistics, G1 and G2. And our target statistics, our observed data, is up here, up there. And then our starting parameters, we're starting at our expectations at 0, 0. So that's where we're starting from. We draw a sample, and you see all the little pink dots there. Those are our sample from that distribution, that starting value. And then we have some sort of trust region, how far we're willing to go away from that eta naught value before we say, hey, I'm not trusting this anymore. I'm not trusting this approximation. And that will and then we maximize within that trust region, and that'll take us over to that second point. Then from that second point, we redraw a new set from that point, and we calculate a new trust region, and we move to the third point. And then at the third point, we redraw another sample and in our trust region, and we maximize to a point within our trust region. So we've hit where we want to go. And so that's the basic idea of sort of bootstrapping your way from a starting value to the maximum likelihood estimate using successive samplings from different parameter values. Okay, so that sort of begs the question. First of all, how do we sample from our distribution? I haven't said anything about that. Second one is, what should the initial values be? Where should we actually start this whole process from? If we start it from really far away, it's going to take a really long time to get there. Thirdly, how do we know when to trust our likelihood approximation? And then fourthly, I'm getting my numbers all mixed up here. And fourthly, are there any better approximations of that log expectation that we saw? Okay, so we need to do a little background on MCMC. How many of people here have ever implemented or used MCMC? Oh, great. That's a very significant portion. So part of this may be a little bit normal for you. So we need a sample from P of t, but we can't actually solve that integral. So suppose that t is just a really long vector of things. That's what our t looks like. Then let's look at just the probability of one of those, conditional upon all of the rest of them being exactly at the values that t is currently. So that's the probability of ti given eta and t minus I, which basically means given everything else. It turns out that that has pretty much the same functional form as the full distribution, except the normalizing constant is an integral over just ti, so a univariate integral. That's something we can do, or a univariate summation if we've got binary data. So like binary data, so the ci is equal to the numerator with that particular ti value set to 0 and everything else remaining the same, plus the numerator with that particular ti value set to 1 and everything else remains the same. So it's just the sum of two things. So we can do that. So that's sort of fine and dandy, but it doesn't really get us where we want to go. We're sampling from t sub I. We want to sample from the full distribution of t. And that's where Gibbs sampling comes to the rescue. Basically, you start with an arbitrary starting value for your t vector. You select I uniform from that vector. Then you draw a replacement for that from the conditional distribution at that I value. And then you rinse and repeat. You do this over and over and over again. And even if you start way away from where your distribution is, eventually what you're going to get is a correlated sample of t's from your target distribution. And that's sort of magic. And I mean, the basic reasons why that happens for the Gibbs case, I think can be best described as, so your P of ti, if the rest of your distribution comes from the appropriate full distribution of t, if your rest of your t comes from that distribution, essentially the new value will also come from that distribution after you replaced it with the random draw from the conditional. So essentially what you've got is as the stationary distribution of your t's is going to be the correct one. I'm not sure if that made sense, but just if it didn't make sense, just consider it magic. Okay, so great. So now we can sample from our distribution. So we can actually apply that algorithm that I talked about earlier. But what about finding the mean value parameters, right? The expectations. And that's where this important sampling thing comes in a little bit. Is so say we have a sample from an arbitrary distribution P1. Then we'll estimate the expectation just by using the sample expectation. And so that's great. But what if we want to sample from a different distribution, P2? And can we use our sample from P1 in some way to get to P2? Turns out we can. It's called importance sampling. And essentially what it is it's a weighted, you do a weighted average of your sample that you got from the original P1. And it's weighted by the ratio of the two probabilities divided by the sum of the ratio over all of your sample. And so that's pretty cool, but then remember, we can't actually calculate our probability distributions. We only know them up to a constant. The fun thing with importance sampling is that those normalizing constants cancel out in the numerator and the denominator, so you're left with something that ends up being tractable. So we can sample from a distribution that isn't even the distribution that we drew from, and we can estimate from that. But it's not a magic wand. If your distributions are similar to each other, then the ratios of the probabilities are going to be about the same. They're about going to be 1 over k, or however many samples you have. If your distributions are different, then some of them are going to be really high and some of them are going to be really low. And that variation causes added variance in your estimates of the expectations. And if your distributions are too far away, then you get basically junk. And it's completely unworkable. But we shouldn't expect everything to work out. I mean, that's a ridiculous thing to expect to work. OK, but how do we know what the variance is? Right? So we know that the variance goes up where our distributions move away from each other. But how bad is it? Can we quantify the variance added by doing this importance sampling? And it turns out that we can. Essentially, there's this thing called batch MCMC variances, or standard errors. And what you do is you take the square root of n. So we've got 10,000 samples here. So we divide it into groups of 100, right? And then we take each of those groups of 100, and we calculate the importance sample within that batch. And then we take that and we look at the difference between our batch means and the overall global estimated mean value parameter. And basically, it's the standard error of that turns into the standard error of your estimate. So we've got mean value parameters that we can estimate around our parameter value eta naught, right? Because we start from eta naught, we're interested in the stuff around it. And we can estimate the standard error of our estimates. And that is what motivates. Yeah.
Do you mind taking a step back?
Sure.
You have data, and now you want to fit the distribution to it, right? The maximum likelihood. That's the goal.
Yes.
So, usually, I would use Markov Chain Monte Carlo now if I basically said, okay, yeah, I've got parameters, I put a prior on those parameters, and then I sample the parameters to get rid of them. You are saying, okay, I could also use Markov Chain Monte Carlo by generating samples and then doing moment matching, and that's basically gives me the maximum likelihood parameters. But what are you sampling over? That's the thing that I haven't understood.
What am I sampling?
The parameters?
No, you're sampling over the data, so T. You're not doing sampling over the eta values, which would be the sort of Bayesian framework. And so you can do Bayesian framework stuff when you can't calculate the normalizing constant. It's a little bit tricky, and it requires something. What was it called? Doubly. No, it was something like doubly intractable, because you can't do the normalizing constant, and then also the parameter values are sort of intractable. But go ahead.
I see. For one set of parameters, you can calculate the normalizing constant, so you wouldn't have this problem. But I still don't see how the data gets in. How do you use the data?
So the data comes in. So with the so the data comes in right there. So that T is your data. That's what comes in. That's the observed network, right? So you calculate your statistics for your observed network, and that's where it comes into the likelihood. And then down here, you have your observed statistics minus your expected statistics given the parameters. That's your.
T, the random variable, basically that is there you plug in the samples from your Markov chain Monte Carlo.
Yes.
Okay.
Yeah. So.
Whenever there's an expectation, basically you sample, and T of small t is the data. Okay.
Yeah. Exactly. Any other questions, comments, concerns?
Can you give us
Yep.
example how the data would look like that you analyze in social?
Sure. I have a small example that will come up in the example section, but basically the example is looking at a monastery in 1969. It's looking at the connections between monks in that monastery. And so what you've got is, and you actually saw it in the beginning, it was that matrix and the X. So the matrix is the connections between monks in a monastery in 1969. Why that's the standard sort of test case for social network analysis, I don't know, but it is. So that's where it comes in. But in larger problems, it would be classrooms and injection drug users and Facebook peoples and that sort of thing. Yep.
At the risk of introducing a potentially significant digression, can you comment on the relationship between exponential families and maximum entropy?
Yes. So the exponential family distributions actually tend to, what they are is subject to the condition that the moment matching is true, right? That your statistics are equal to the mean value parameters. And that's the only assumption, no functional forms or anything else. Subject to that, maximum likelihood distributions have maximum entropy over any sort of distributions. And what that means is that they're uniform. So as uniform as possible, subject to the constraint that the statistics are matching your data. And what that allows for is, it's sort of in a way, you can think of it as you're trying to make as little assumptions about your data as possible because you're not introducing added, sort of probability density in places that the data doesn't support. And so from the machine learning standpoint, often it's talked about, they're motivated from exponential families are motivated from maximum likelihood. From the statistical standpoint, they're often motivated from the data generation process, thinking about the data generation process and then getting to them that way.
When you say motivated by maximum likelihood, do you mean motivated by maximum entropy? Or
Motivated by maximum entropy. Yeah, so, okay. So how far around our parameter set are we willing to get? Geyer-Thompson suggested eta minus eta naught as bounded by some epsilon. That is a pretty horrendous one. It doesn't. I mean, it's very problem specific. What's the scale of your etas depends on your problem. And so it can work, but it's very dependent. And some of your etas may have much larger scales than others of them. So that it can work for a particular problem, but is not really a general solution that we're looking for. The sort of package that is sort of the gold standard for doing exponential random graph models, ERGM, uses the criteria that the likelihood ratio estimate that we've done is less than 20. And essentially what that's saying is that as you get further away from your true maximum likelihood, or from the eta naught, what happens is the poor fit between the estimated and the true is evidenced by the estimated one diverging. So this is sort of like saying, hey, this is diverging probably at this point, so let's cut it off and only consider stuff that's in that sort of immediate neighborhood. So those are two heuristic ideas, and the ERNM one has been implemented and used for many years, and so that's a pretty decent one to go by. The one that I used for my research was different. I wanted to come up with sort of a principled heuristic method for determining that trust region. And essentially, the idea is that if we have poor estimates of our mean value parameters at the eta values that we're considering, then we shouldn't trust our likelihood, because we certainly can't determine the first derivative of it. So we should say if we've got poor estimates of our mean value parameters, then we should bound it by that. And remember, our mean value parameters are just the importance weighted versions of our statistics, right? So we've got sample from eta naught, and we want it from to estimate the mean value parameters at eta. So we import the sample to get out there. And remember that we can calculate the standard error of that estimate. So what we can do is we can say, OK, well, we'll just limit the effective sample size of, if the effective sample size of our estimate out here is like really low, then we shouldn't trust it. And so the effective sample size is simply the ratio of the estimated standard error of the mean value parameters divided by sort of a simple random, what the standard error would be for a simple random sample estimate of that parameter at eta naught. And so you do that, and you set the likelihood constraint to say, all right, let's just, it actually works at a very small level. So if you just say the effective sample size needs to be better than something like 4, then you are pretty good. And so that gives us our trust bounds. The other thing we need is starting values. That one is the sort of best practices to do pseudo-likelihood estimation. So remember our distribution of P of Ti that we could calculate, but we couldn't calculate the full one? Well, it turns out that doing something really stupid, which is just assuming that each of the T's are independent and multiplying their probabilities. So your log probability looks like the sum of the log of the probability at each of the T values. And maximizing that actually does a pretty good job at getting you in the neighborhood of your true values, or the maximum likelihood values. So that is a really good place to start. So you basically use something like Newton-Raphson, or a standard technique for optimizing functions that you can actually write down to come up with the maximization of that log pseudo-likelihood, and that will give you your starting values for your eta. So great. So we've got some starting values. We can calculate our trust regions. So all that's left is wondering whether our simple thing, which was estimating that z by a simple random sample, whether that, or as the simple mean, whether that's the appropriate thing to do or the best thing to do. It turns out that that log expectation that we've been dealing with is actually a fairly well-known quantity. It's called the cumulant generating function. And essentially, for notational convenience, we'll call eta minus eta naught eta prime. And essentially, if we take the Taylor expansion of that exponential, then we get the right-hand side there. And then distributing out the expectations, taking a further Taylor expansion of log 1 plus x, where x is the rest of that stuff, gets us this ugly-looking thing right here. if you rearrange all the terms in the appropriate manner, you get that log expectation is equal to the sum from 0 to infinity of the ith cumulant of I divided by I factorial. How many people in here know what a cumulant is? Sweet, so everyone knows. No, just kidding. So the cumulants are related to the moments of a distribution. They're actually sort of reparameterizations of the moments. So the first cumulant is the same as the first moment, central moment, which is the mean. So first cumulant is mean, first moment is mean. The second one is also the same. It's the variance. First moment is the variance, first cumulant is the variance. The third moment is the skew. And the third cumulant is related to the skew, but it's different. So it's a functional transformation of that. So what you end up with is basically a reparameterization of the moments, but there's plenty of software that will calculate that for you. But we can't actually calculate the true values of those because obviously we can't calculate our distribution. So how can we calculate those? A simple thing to do is to propose to estimate that by the first couple sample cumulants. So basically we're just taking the first couple terms of that using the first couple cumulants, and that will give us our estimate. There's a trade-off to be had here. As you let m go higher, the sample cumulants become more and more variable, right? The higher order terms, you've got x to the 5th to the 70th. Those are going to have higher variance because you've only got a sample. And the other trade-off is the fact that you're adding terms to the Taylor expansion. So the more terms you add, the better the Taylor expansion is. So there's some point there where those two sort of cancel out, and you want to know what point that is. We've had a lot of success with using 2 and 3, really. So it actually, the second one is the mean plus the variance over 2. And that's actually called the log normal approximation. Because if eta prime times g is normal, then that's the actual true one, because the higher order moments and cumulants of the normal distribution are 0. And then the third order approximation is actually what I use in my package, maybe just to be a little different. But let's take a look at that. So consider a binomial model. So we've just got e to the eta times the sum of ti. So ti is a vector of Bernoulli variables, and we've got 100 of length 780, and we observed 272 successes. So that leads to an MLE of eta equals negative 0.625. Okay. Because this is such a simple model, we can calculate the normalizing constant actually directly because of the independence between those Bernoulli variables. And that's important because we're going to want to see the ground truth versus our different sort of cumulant function approximations. So here, hopefully, I'm not sure if everyone can see this, but essentially what we've got is the ground truth is the black line, and the z infinity, which is actually, if you take all of the terms, it converges to that simple naive mean that we were doing in the beginning. Z infinity is up here. So we can see that it's not doing well at capturing this log likelihood. The log normal approximation is this guy right here, and then the third and fourth order approximations get pretty close to what the true value is here. And this is drawing a huge sample of 100,000. Well, huge from most practical standpoint, sample of 100,000 completely independent variates for our sample estimation at the maximum likelihood point. So eta naught is equal to the maximum likelihood. So this is really designed to actually give the simple sample method the best benefit of the doubt, and it's still not performing particularly well. When we get farther away from the true eta value, so we're drawing from eta naught equals 0, the simple method diverges quite poorly, and so does the fourth order version. The log normal and third order method get pretty close to our true ground truth at curve of the log likelihood. All right, so the one thing is that here we're dealing with binomial data. So as you get binomial data with higher n's, it's converging to normal, right? And we said that the log normal approximation does best when you've got a normal distribution. So maybe we're giving the log normal too much credit here. So we're going to look at a really small scaled down physics problem. So we've got a toroidal lattice. That's just a lattice with connections connecting around this way and this way of nodes with binary data. And we're going to do an icing model on these. This is modeling magnetism. And I won't go into it too much, but basically it's got two parameters. One is the number of connections between like magnetisms, and the other is the number of nodes with positive magnetism. And we see that it's skewed, and we actually got a little bimodality over there. So this is probably not going to be good for the normal or the log normal approximation. But it's very small. This is a very small and scaled down problem, and I feel that there's more simulation studies that should be done, perhaps by a master's student or something like that. But here's the results. So if we're starting looking at the second parameter value with the first parameter value set at its MLE, and we draw from so the MLE is at 0.2, 0.8, and we're going to draw from 0.2, 0.11. So we're pretty far away from where we should be. The top one that's not close, that's the log normal approximation. The third order is right here. And then the fourth and sample do really well on this one. And then switching it around and looking at the other parameter value. So we set the second parameter at 0.8, and we look at the first parameter. We see again that the log normal isn't doing so well. The third and fourth are doing pretty well, and so is the sample. So basically, the takeaway from this is that I think that the third order one strikes an appropriate balance between those two competing problems that we were talking about. Okay, so that's the entire theory of doing maximum likelihood in exponential families. We have any? I'll do an example, but do we have any questions on that? Have I blown through it just too completely quickly? Maybe a little bit. Okay, so we want some real data. So here's that data from 1960s with monks. So there's a sociologist who just went to this monastery, Samson, for his PhD dissertation. He just sat there and observed these monks and asked them questions and stuff like that. And this is one of the social networks that he came up with. And as you can see, it's got sort of three clusters to it. And Samson named them the young Turks, the loyal opposition, and the outcasts. Those are the outcasts. I forget which one of those is the loyal opposition. But the outcasts are pretty clearly outcasty. So that was so there's 18 of them. So this is a small problem. And it's small because I want to actually do something live here. But it's a small problem, but it's still, if you consider both the ties and this grouping variable random, you've got a t of length about 5,000, right? So it's about 5,000 correlated random variables. And if you wanted to calculate the normalizing constant on that, that would be something like 10 to the 100 or something like that. So even small problems are just completely ridiculous. We're going to do a simple model. Both, we're going to do an ERNM model, because that was what my dissertation was on. So both y and x are going to be random here. We've got a first term, which will be the number of edges in the network. And so that will make sure that the edges are at their sort of appropriate value. The second one is a measure of homophily, which is the tendency of friends to be like friends in the same group. And that's got this weird functional form that's actually fairly computationally complex to evaluate. But basically this avoids some phase transition-y type stuff that happens if you do more simple stuff. And then the second two are the counts in each group. So the third parameter is the counts in the loyal opposition group. The fourth parameter is the counts of monks in the outcast group. And then the next one is omitted because otherwise you'd have identifiability issues. OK, so if we've got so if we bring in this data, we see that it looks something like this. So we've got our groups here. I mean, they're positioned a little bit differently, but that's the essential thing that we've got. And we want to fit a model to this. And so basically we just say, all right.
Question on the data. So what sets the lengths of those?
Yeah, I have some question.
Well, what just happened there?
He asking what is the distance between those points?
Oh, sorry. Oh, this guy? Well, maybe someone can do this and I'll answer. So what was the, sorry, what was the question?
What sets the lengths of the segments in that lat?
Oh, so that's done using, I think that one is done using a physics algorithm, just basically treating them like springs. So this one is, it's just a layout. Yeah. So, but
Are made by friends and then lengths are just to help display?
So this layout completely ignores the clustering. The clustering is just sort of apparent, but it treats the nodes as having springs attached to them and then having gravity towards friends, I think. But I'm not sure. It's just one of the standard layout algorithms for networks.
And that's just for display purposes?
Yeah, this is just for display purposes.
It is all at the same weight. There's no edge weight.
No, there's no edge values. This is a non-valued network. So there are ways to do valued networks. Pavel Krivitsky has come up with a lot of interesting research in that, and et al. Have come up with a lot of interesting research in that area. But this is just with valued, unvalued 0-1 ties. But it's directed, so a tie from one does not have to be a tie to the other. Yep.
Where did the cluster assignments come from? Was that just based on the work of that sociologist?
Yes,
Yeah, okay.
it was. And I don't think we're going to have time, but what I wanted to do was do a missing data problem and treat those as missing data and estimate those using these models. But I don't think we're going to have time for that, so sorry. All right, so basically we're just doing a model here with edges, homophily, and the counts in each group. And we're going to say that group is a random variate. We're going to make it very verbose. You know, you'd think that I would remember these from a program that I wrote, or helped write, anyhow. Okay. So we are going to just fit this model and watch what happens. So we're going to set this kind of slowly so it will you'll see it. So we're drawing samples from a starting value sort of pretty far away from where we want to go. So it draws these MCMC samples from the 4 different parameters that we have in the model. It's maximized subject to the constraint, and now it's moved to a different value, and it's done the MCMC on that different value. And in the next iteration, we'll continue that process and see we're still improving our log likelihood estimate. So the log likelihood has improved by 16. It's by 13 here. And it will continue to improve. Maybe I set this to go too slowly, but and we've also got this thing called the scaled gradient, which you can see is going down. It's a measure of how far we are away from the moments that we've said we are. It's improved a little bit here, so maybe we're getting pretty close. And you'll also notice that the range of the nodes has shrunk significantly. So here we are. So the range of these last 2 have shrunk significantly. That's because there's a lot of homophily, forcing these to be about at their observed values. So we've got our maximum likelihood estimate. And we can take a look at the summary of that. We get thetas and standard errors using Fisher information, which I haven't presented here, p-values. And this is a generative model of this network. So we can actually simulate hypothetical monasteries from this. And we can also look at the probability of different relations. I think that may be sort of all the time that we have for this. I did want to show you that you can deal with missing values and in a way that leads to novel sort of latent class models for networks. But we'll just have to imagine that that's there.
What's about monasteries? We'll take that on faith.
Yeah, exactly. Excellent. Yes?
So you're basically using gradient descent to find the...
Right. So within each of the trust regions, you can use gradient ascent or really anything. The computationally complex things happens with the MCMC draw. So you can use Newton-Raphson is actually, I think, we use the trust package in R to do the maximization. But really anything, any sort of maximization algorithm which will actually get to the maximum eventually is perfectly fine. The computationally complex thing is in drawing the MCMC samples.
What constitutes one monk knowing the other?
So that in the original data, I believe, and I'm sorry that this is being recorded because I could be totally wrong. I believe that it was a conglomeration of 3 time points, and if the monk said that the other monk was a friend of theirs over those 3 time points, then it was considered a tie, and if they didn't, then it wasn't. So, I mean, the basic idea here is that, I've given network examples, but essentially, any maximum likelihood problem within a certain sort of range of scalability is able to be estimated using this problem. It allows an incredibly flexible method for fitting your data. And in terms of scalability, it goes up to sort of millions and maybe hundreds of millions of the length of t, and then but not quadrillions. Yep.
So
Sure.
But what does that physically mean about it?
So, like, I guess one of the things that we can see here is that we've got an extremely significant homophily term here. So we can say, yes, those clusters that we sort of saw came out of that physics problem were justified by the data. And there's a lot more complex things you can do, but generally you need more complex models, but I just wanted something sort of simple for illustration here. Yep.
I missed the formulas before. Can you say a few words about just the interpretation of the other parameters?
Yes. So edges here, if this term was 0, then that would mean that there's as likely to be an edge as not. So if 50% of the edges were true, or 50% of the diodes were edges, then that would be 0. This is negative, so it means that there's many fewer. It's a sparse graph, which, yeah, so the edges is a measure of density. And then the two node count terms here are measures of the number of people in each of those X groups, right, in each of the groups. So we're thinking that, I mean, if you looked at this at sort of monasteries in general with like a sort of superpopulation, scope on it, that not every monastery would have exactly the same number of groups in each of their clusters. And so that's sort of taking into account that uncertainty. Yes?
So I see like forward distribution, but are they supposed to be like marginalized under like the category of the Young Turks and the three categories, or is like describe the whole population?
Sorry, maybe I'm not quite understanding.
Are the distributions supposed to be fit to each of the three categories and marginalized under category, or are they just those distributions for the whole population?
They're fit for the whole population as a whole, taking into account the X values, which are the groupings. Yep.
I wonder if you could give an intuitive summary of the approach. So from what I understand, you want to do maximum likelihood. You can't compute the normalizing constant. And so what you do instead is you sample data from the distribution with some parameter setting, and you see if the moments match. If they do, you're doing well. If they don't, then you move around in the parameter space. And then somehow you form a cluster region in which I think you have some analytical approximation for which you then can do graphs in, but I'm not sure. You could just fill in to the
Sure. So the high level thing is that exactly as you said, so you want to do maximum likelihood, you can't compute the normalizing constant. You can sample from the distributions, and you can approximate around your sample parameters, the one that you took the sample from, you can approximate your likelihood function. You maximize that approximation.
And what was the basis of that likelihood approximation in this region?
So the basis was so it was this right here. So you've got your true log likelihood right up here, right? Now, if you have a sample, you can approximate that second term, which is intractable, by the sample mean. And so that's this guy right here. So you approximate it using the sample mean or one of the other approximations that we talked about later. And that becomes the basis for your likelihood approximation. But you've got a mean of e to the something. So as eta goes away from eta naught, the variability in that's going to increase. And so that's the basic idea, is that you can't trust that approximation beyond a certain level. And so what you have to do is you have to iteratively maximize. So you maximize within your trust region, and then you draw another sample. You get another trust region, and then you maximize within that one. And that gets you even closer, and then you maximize within that one. And sooner or later, you're going to get to the maximum likelihood estimate.
Is there any bounds that you can show how far off you can? Are you always? I mean, I don't think you can show that you're always improving that likelihood here, right? I mean,
Oh, well, yeah, you can show that you're increasing the approximation of the likelihood. So if your approximation's...
Also the approximation, you're increasing that, yeah.
Yeah, so if the approximation is any good, then you're increasing it. And the approximation is good around the eta naught value. So if you have converged and you're showing that the maximum is at the point that you're at, then you're good to go. Yes?
I don't understand in this specific example, what's the sample that you're doing? Because you have such a, so is the sample trying to take only 17 and guessing based on that, trying to see if those 17 you can expect for each one of them the correct cast?
So you can do a lot of different things with this. So the model that I showed was, it was based on, this is the data ignoring the NAs there. The models create a generative model of your data. So what you can do is you can use that to simulate hypothetical data, or you can look at maybe what's the other guy given the rest of the data. So you can conditionalize it on that and look at those conditional probabilities as well as sort of how well your prediction's doing.
What did you do here? You can't